So I'm living in Switzerland now, and I'm trying to be really punctual for everything, but I just can't seem to get it right. So anyway, thanks. Hey, I want to start off just by acknowledging the Aotearoa New Zealand Antarctic Science Platform. So this is long-term base funding for us, and it's really been a game changer. And today I'm going to be talking about Kamb Ice Stream. So this is one of the 5 ice streams that feed into the Ross Ice Shelf. And it's really distinct because it's stagnated around 160 years ago. And this stagnation has caused a lot of accumulation upstream on Kamb, and that currently offsets about a quarter of the mass imbalance of West Antarctica. So it's a really significant player in West Antarctica. Now, offsetting, it's not a reliable mechanism. So this stagnation is thought to be due to changing water routing at the base of the ice stream. So we went out to investigate what's actually the flux of water coming out from beneath this part of the West Antarctic ice sheet. Okay, our viewpoint here is from out over the Ross Ice Shelf, looking towards Kamb Ice Stream there. And what I've overlain on the image is Mauro Verde's new subglacial routing and flux for subglacial water. So the black spot there is our drill location. So you can see the flow beneath Kamb Ice Stream coalesces into one main trunk that then emerges at the grounding line. I also want to point out the blue dots there, which are the subglacial lakes from the Livingston inventory. And also those red dots, one of which is a past drill site we've occupied, and the more seaward one is actually the Swace to Sea drill site. So hopefully what I'm saying has implications for what we'll find there. Okay, let's see how this goes. Again, we're looking from, this time it's a perspective view from upstream. And in gray here, we're seeing the base of the ice shelf. In white, those contours are the surface elevation of the ice shelf. You can see the dotted dashed vertical line there, that's where we've drilled in. And we've actually drilled into the head of this emerging subglacial channel. So we're about 4 kilometers from the grounding line proper, where the open ocean, or where the cavity starts. And we're about 750 meters from where that subglacial water first emerges, mixes with ocean water, and is able to melt this really impressive channel. Okay, so here's the channel itself. We were able to drill in and then lower a rotating altimeter. So we're actually imaging the sides of the subglacial channel. We're beneath about 500 meters of ice. This channel is about 240 meters high. At the base, 100 odd meters across. It has this odd keyhole shape. So yeah, the sides are almost vertical, and then we sort of balloon out as we go up. Plotted there is the scaled version, and blue arrows, these are our velocities. So these are our profile velocities, and we can see the flow is quite estuarine. I'm also plotting turbidity there, and salinity and temperature. So we've got warm, salty water coming in at the base. It's then mixing and rising as it meets the fresh water coming from underneath the ice shelf, underneath the ice sheet. And then that's rising, and it's coming back out as this turbid plume. So this nose here is that turbid plume of fresh water coming out. I should point out how hard it is to get estimates of subglacial flux from beneath the ice sheets through observations. So to my knowledge, this is only the second time this has actually been imaged, and the first time beneath the deep interior of an ice shelf. Okay, so we can combine these observations. We can take that channel cross-section. We can then add on our velocities and our temperature and salinity profiles, and we can look through a mixing model at how much of this water body is meltwater, how much of it is the incoming high salinity shelf water from the ice front, and how much is actually flux from beneath the ice sheet. And the flux quantities we're getting are really surprisingly low. So this part of the ice sheet, we're only getting about 0.7 meters per second, cubic meters per second actually coming out. Now that's more than a fire hose, but it's not a lot more. This is like a culvert. So I think this was our first indicator of what we think we know from the lakes. People like Max Siegfried have done a really nice job of showing this, we shouldn't expect the flow to be steady state, right? We should expect this to come in bursts. Now, I should point out, for the oceanographers, this temperature salinity plot is quite spectacular too. So we've got our source water coming in here, coming down a really nice Cascade mixing line, and then a really marked deviation that coincides with the high turbidity water coming out from beneath, which then mixes and returns again to a nice Cascade line. I've totally lost track of time, so just give me 5 minutes, thanks. Great. We had IceFin with us. So IceFin went down through the borehole, and what I'm showing here is their swath of the base of this channel. So that's our borehole site there, and this is heading up channel. A really interesting feature for me as a glaciologist is this incised channel in the base of the main channel. So we think that's the previous sub-ice sheet channel where water was routed, actually a canal in the sediment, and then over the top of that we've formed this more impressive melt feature. We were able to core sediments from the base of the channel, and I think this is where we then link back into the lakes record, because we can see steady deposition at the top, and then we have these quite distinct deposit events. This is only 53 centimeters in all. We see 3 significant events coming through, some of which with large class sizes, indicating relatively high energy deposition, graded deposits, and also very distinct provenance, so provenance shifts. And that's telling us that the water might be coming out in the same spot, but the geology is being sampled from different parts of the ice stream bed. So that's, I consider that quite a significant finding. Not only are we temporally variable, but we're spatially variable. Yeah, this is imagery from IceFin from the base of the channel. So we've got very soft sediments. These are sediment tracks in the sediment. We actually saw this creature crawling up. We've got a rain out of lots of sediment, but we also have meter scale angular boulders that are just sitting around in this channel, indicating, to me, very high energy at some point in the past. Maldo Verter's done some really nice work on where this water most likely comes from. So we can now look at catchments for these water sources beneath the ice sheets. So these are distinct from the ice flow catchments we more commonly think about. And he's done this in a probabilistic way. So the catchment at this location mainly sits in the bottom of Kamb, but if we perturb what we know about the surface and the bed a bit, the catchment gets much bigger. It cuts into the top of Willans' catchment, and it can be a much more extensive area, sampling more subglacial lakes. Now, there are real impacts to this subglacial flow. Aside from the stagnation story, which is something that's happening over hundreds of year timescales, we're also seeing surface mass balance down wasting. This is over 1.5 meters per year at this site as this melts down. And we're also seeing the associated melt out on the ice sheet itself. And I would say this is one of the more significant sites of impact on the ice shelf, where we see a subglacially sourced channel, then leading to really significant ice shelf damage downstream. So this site in particular, we've got tens of kilometers of damage extending, associated with quite dramatic thinning of that part of the ice shelf. And that brings to mind the sort of channel crevassing hypothesis of David Vaughan and others, and also the secondary flow and that balance between secondary flow and actual destabilizing of an ice shelf too. Great. Yeah, and this has happened in the past. So this is a great site on Kamb because we can actually see isolated versions of this channel when the grounding line was actually at other static positions. So this is definitely a spot where the grounding line sits there and then it steps back very quickly. So we have these isolated truncated channels that actually cross-cut flow features, which tells us that all of this has occurred within the last 160 years since stagnation. Okay, so I'll stop there. We've got steady state subglacial discharge, which is surprisingly low, orders of magnitude below other model estimates, multiple discharge events that source sediment from different parts of the ice stream bed. The catchment size varies significantly, and this is a fairly significant supply of sediment at this location. With bigger events, who knows how big that sediment will be distributed. Thank you very much. Oh, and there were fish. Yep. Yep.
Thank you, Huw. Any questions?
Hi, yeah, thanks for the talk. I think this is just, I missed the initial figure where the location is, and I just wondered how far away from the grounding line the borehole was.
Yeah, so we're about, depends how you define the grounding line, doesn't it? If you're talking about where salt water is, we've got salty water. But the grounding line proper, as a coarse definition, is about 4 kilometers downstream, and the subglacial input's about 750 meters upstream. Yeah.
Yeah, thanks for the talk. It's amazing stuff to see. I'm just thinking of the boulders and the former channel. Brings to mind Jokelhops and kind of subglacial bursts. Is that something within your outburst, you know, lake bursts?
Yeah, I mean, Matt would be a great person to talk to this about, but I think the catalog we have of subglacial lakes is very incomplete, isn't it? There's a lot of small things that we don't see, and there are big things that we haven't had enough time to see. So I think potentially this is those sort of outburst events, shifting large quantities of sediment and boulder scales. Yeah. Thanks.
So sticking with the same sort of theme, we've got Matthew Seafrick now, talking about tracing